in this half of our introduction to vectors, we're going to see how trigonometry is going to play a role in dealing with vectors. Okay, so in our first example, we are asked to determine the components of our vector, and we want to round to the nearest hundredth. So a few things, and then we're given this picture here, and some of the things that I see is that here's our vector v, and it's drawn on here, and this is labeled with 3 meters, and that 3 meters tells me that the magnitude of our vector is 3, or 3 meters in this case. So the length of this arrow is a length of 3. And we're given an angle of 130 degrees. Our textbook calls this the direction angle. And in our textbook, when they talk about a direction, when our author talks about a direction angle, your author is talking about an angle measured from standard position from an angle of 0 and measured counterclockwise until we hit our vector that we're looking at. In context, when we're talking about actual applications, there will be times when you don't have an XY plane, and so we might not necessarily talk about this direction angle as much as an angle relative to some line. So we'll see some of those examples on Wednesday. Okay, so we're given an angle and we're given the length of our vector, and our job is to find the components of our vector. So if I take this vector and I break it up, I draw this triangle, and I have the x component of our vector, which I call vx, and I have the y component of our vector, which I call vy. So in the end, we want to write down a vector v that has an x component and a y component. So if we can find values for vx and vy, then we'll be done. Okay, now to come up with these values, there are a variety of ways that I can do this. The way that I personally would like to think about this is I like to think about this triangle that I've created and pull it out of the picture that I have here. So here is our triangle that we have. And in this triangle, I know that the hypotenuse has a length of 3. And the other thing I know is that once I have this angle of 130 degrees, the reference angle that is in this triangle will be a reference angle of 50 degrees because the total is 180, and if we go 130, I need 50 more to get me to a full 180. Okay, so in our triangle up here, we have an angle of 50 degrees, and we know what the hypotenuse is. So I want to be able to find the vertical side and the horizontal side. And relative to the 50 degrees, the vertical side is our opposite side, and the horizontal side is our adjacent side. So using some trig, I'm going to start by finding that opposite side. And I know that if I'm looking for the opposite side and I have the hypotenuse, the sine function is opposite over hypotenuse. So I know that sine of 50 degrees is our opposite side over our hypotenuse, which is 3. So I can solve this equation for the opposite side, and I have 3 times the sine of 50 degrees is equal to the opposite side. So let's go over to the graphing calculator and type this in. Okay, so I'm going to type in 3 times the sine of 50, and I'm going to hit enter. And I got negative 0.787. Now look, I know I'm looking for a length, and that should be a positive number, so something is wrong here. And here's what's wrong. For the last month, probably, of class, we have been talking about radian measure. And suddenly we're talking about degrees again. So I need to remember that when I go into my calculator on these problems that we're working on with vectors, if our angle measurement is in degrees, I better make sure that my mode is in degree mode and not in radian. So I better change that right now before we go any further. Okay, So now my calculator is in degree mode, and we can try this calculation again. Franklin's going to check it out for us and make sure that we're doing this correctly. So we have 3 times the sine of 50. Okay, that looks a little bit better. We at least have a positive number now. So 2.298, I can round that off to 2.30. So our opposite side is 2.30, and so that's going to be my Vy value, my y component. Okay, let's do our x component now. So to find the adjacent side, I want to find the adjacent side. I'm given the hypotenuse. Cosine is adjacent over hypotenuse, so we can write down cosine of 50 degrees equals adjacent over hypotenuse, which is 3. Multiply both sides by 3, and I'll have 3 times the cosine of 50 degrees is our adjacent side. So this one, I already know I'm in degrees over here, so we can just type in 3 times the cosine of 50 degrees, and we get 1 point, rounding off, 1.93. So our adjacent side is 1.93. So I come back over here and I'm ready to write down my x component. Our value is 1.93, but I have to be careful. Because our vector is in quadrant 2, the x values are negative, which means that our x component needs to be a negative number. Okay. So once I make sure that my signs, SIGNs, are correct, then I can write down my components. So my vector v is negative 1.93, comma, 2.30. And so we found our components. Okay. Let's take a look at another example. All right, in this example, we would like to determine the components of a vector w, and we are asked to give exact values. Now, as soon as I see the words give exact values, that means I'm going to want to do this one by hand with no calculator approximations. All right, now here's our picture that we are given. We are given a vector w, and this vector lives in quadrant 4, and we have a measurement of 4 centimeters for the length of our vector, and we are told that the direction angle is an angle of 300 degrees. Okay, so we want to find the components of our vector w, so we are looking for our x component and our y component, and I can draw them on this picture by creating a triangle just like we do a lot in trig. And so we have our x component is our horizontal portion of the triangle, and our y component of our vector is the vertical portion of our triangle. Okay, so something I notice here is that our outer angle, our angle from the start all the way around, is 300 degrees, which means that to make a complete circle of 360, we are short by 60 degrees. Okay, so our reference angle here is 60 degrees, which makes me happy because then I can use my 30-60 right triangle stuff and I can come up with exact values. Okay, so I'm going to draw this triangle over here. The reason that I separate this triangle from the picture is because in the picture, the lengths of my sides have signs, S-I-G-N's, to them, whereas when I'm calculating the lengths on the triangle, all my lengths are positive. So I'm disassociating the triangle from the picture so that I don't have to worry about the signs, S-I-G-N's, of each of the legs. Okay, so we have a 60-degree angle here. We're told that the hypotenuse has a length of 4. That's the magnitude of our vector. And from our angle of 60 degrees, we have an adjacent side and we have an opposite side, and we want to calculate both of those values. So let's start with the opposite side. So I know that sine is opposite over hypotenuse, so the sine of 60 will be opposite over 4 in this case. Multiply both sides by 4, and I have 4 times the sine of 60 equals our opposite side. Now here's where you get to make a choice. And your choice is, do you know what the sine of 60 degrees is? You might have that memorized. You might have a photographic memory, and you might have a unit circle drawn in your head, and sine of 60 would be the y value of the 60-degree or pi over 3 angle. Or you might draw yourself a real quick little triangle over to the side, our sort of mini 60-degree triangle, where we have 1, 2, and square root of 3 as our 3 sides. And I know that the sine of 60 is opposite over hypotenuse. So for our 1, 2 square root of 3 triangle, sine of 60 is opposite root 3 over hypotenuse of 2. So you can get that value from drawing the little triangle or memorizing the unit circle, or however you want to remember or figure out the value for sine of 60. That is your choice. Okay, so we now have 4 times the sine of 60. So that's 4 times root 3 over 2. And that's an okay final answer, but we can clean this up a little bit. We have 4 over 1 times root 3 over 2. And I can reduce some things. I can cancel a 2 on the top and the bottom, and that's going to leave me with 2 times root 3 as our opposite side. Okay, so in our picture, the length of this wy, or the y component, is 2 times the square root of 3, but because the y value is on the negative y side of things, on the bottom half of our graph, I need to have a negative in front, because the sign, S-I-G-N, of our y component is negative. Okay, so that's our y value, and now we want to figure out the x value, and so that is our adjacent side. And when I'm thinking about my 30-60 right triangle, and I'm looking at my 60-degree angle, adjacent over hypotenuse is cosine, so we have cosine of 60 degrees is adjacent over hypotenuse, which is 4. Multiply both sides by 4. And so I have 4 times cosine of 60 degrees is our adjacent side. And I have my little 30-60 right triangle down here. If I didn't, I could redraw it. But cosine is adjacent over hypotenuse, so that's 1 over 2. So I have 4 times 1/2 is our adjacent side. 4 times 1/2 is 2. So our adjacent side is our x component. The length of that is 2. And because it's on the right side of the x-axis, that's a positive value, so we have a positive 2 for the x component. Okay, so we've now broken up our vector into its x component and its y component. So our vector w is the vector 2, negative 2 times the square root of 3. Okay. Now, just as a comment, and this is you'll see much more of this on Wednesday, one of the things that these numbers say are, if you are a person who is starting at the origin and you walked at this given angle for, okay, we're talking about centimeters, so maybe this is more like a bug walking along this, instead of person might be more like kilometers, but at any rate, you've got this bug that's walking 4 centimeters in this direction. That bug's going to land at this location at the end of that 4 centimeters. On the other hand, the bug could walk 2 centimeters to the right and then 2 times the square root of 3 centimeters down, and that bug's going to get to the exact same location. We've taken this diagonal line and broken it into a horizontal direction and a vertical direction. Okay, so we've seen 2 examples where we are given a magnitude and a direction, and our job is to find the x and y components of the vector. We also want to be able to work in the opposite direction, that given the x and y components, we'd like to be able to identify the magnitude as well as the direction, which gives us our orientation. So we're going to take a look at another example. Okay, in this example, we are asked to find the magnitude and direction angle and we are asked to find our magnitude and direction angle to the nearest, well, the angle to the nearest tenth of a degree. We are given the vector v is the vector -7, 24. Okay, now right away I can immediately find the magnitude of this vector. I don't need to have any sort of picture. It doesn't really matter what the vector looks like. And to calculate the magnitude, I take the x component, -7 squared, plus the y component, squared, and then I take the square root of all of that. So -7 squared is 49, plus 24 squared, I think 24 squared is 576, I'm not sure. But then when you add them together, you get 625. So we're taking the square root of 625, and the square root of 625 is 25. So the length of our vector is a length of 25 units. Magnitude of v is 25. Cool. Okay, now we also want to find the direction angle. And finding the direction angle can be done without drawing a picture, but for me, I think it's really intuitive and really much more helpful to have a picture. So I'm going to draw a picture of our vector v, and like we've been doing in all of these examples, I'm going to draw my vector so that I'm looking at the position representation, meaning that the tail is at the origin. We have -7 in the x direction. Now I'm going to mark by values of 5 because this positive 24 is pretty big. 5, 10, 15, 20, 25. Okay, so -7 is about here in the middle, and so -7, and then we're going to go up to 24. So here is our vector, our rough sketch of our, oops, I missed my point. So now I've got to redraw it. That's all right. If I'm going to redraw it, I'll do it in a different color. There it is. Much prettier anyway. Okay, so here is our vector v, and our vy is 24. That's our y component. And our x component, vx, is -7. Okay. Now, we want to find the direction angle, which is the angle, our textbook defines this angle as the angle from the positive x-axis measured in a counterclockwise direction. So we want the angle of theta, which starts over here in the positive x direction and ends on our vector v. Now, in my opinion, it makes a lot more sense to find this reference angle. I'll call it theta prime. And if we find that angle, then our angle that we care about is 180, take away the reference angle. So we're going to focus on finding the reference angle, and from there we can figure out what our main angle is going to be. Okay, so here's our triangle. And I'm taking the triangle out of the diagram because I don't want to worry about the sign, SIGN, of my x or my y component. I want all of my sides to be positive. So we have 7 and we have 24. And our job is to find this angle, which we're calling theta prime. Now, when I look at this triangle, what I see is that I'm given the opposite side and the adjacent side. And so when I think about the trig functions, I think about tangent, because tangent of an angle is opposite over adjacent. So in this case, tangent of our reference angle, theta prime, will be opposite, which is 24, over adjacent, which is 7. Okay, now to find the angle, what I need to do is I need to flip-flop this equation. At the very beginning of the semester, we said we can apply inverse tangent to both sides, and many of you said, what is this inverse tangent thing that you talk about? But now we've talked about these inverse trig functions as graphs, and when we're talking about ratios that are positive for inverse tangent, inverse sine, or inverse cosine, our angle that we get as an output will be an angle in the first quadrant. In other words, an acute angle. So I can apply these inverse trig functions to positive ratios really kind of sloppily because I know that my answer is going to be an angle between 0 and 90, or 0 and pi over 2. Okay, so I'm going to apply inverse tangent to both sides. And so what we have is we have our angle is the inverse tangent of 24 over 7. So the input into our inverse tangent is a ratio of sides, and the output will be an angle. Now, this ratio of sides, opposite over adjacent, is not a set of numbers that I recognize as one of our special triangles, which means to come up with our value, I have a choice. I can go to my calculator, or I can go to an old school trig book and look up a bunch of tables. But I think our best option is to go to the graphing calculator. So let's take a look. Now, I know that in the end, I want to make sure that my answer is in degrees. So I make sure under the mode that my calculator is in degree mode so that my output will be answered in terms of degrees. And we are going to look at inverse tangent of 24 over 7. And we get 73.739 blah blah blah, and we're asked to go look at the nearest tenth of a degree, so we're going to round off to 73.7. Okay, so our reference angle, theta prime, is 73.7 degrees. So that's this angle right in here. The angle between our vector and the negative x-axis is 73.7 degrees. And that tells me then, if that portion is 73.7, then our angle that starts on the positive x-axis and swings over to our vector, that theta is going to be 180 minus our 73.7. And when I calculate that and I do that subtraction, I end up with an angle of 106.3 degrees. And that kind of makes sense to me because when we drew this angle is more than 90, but not a lot more than 90 degrees. So 106 is not that much more than 90 degrees. So just by the picture, it gives me sort of a sense of security that my final angle is a reasonable value for our direction angle. Okay, so in conclusion, we have that our vector v has a magnitude of 25, and our direction angle of theta is 106.3 degrees. And that was what we were being asked. Okay, so today we've seen an introduction to vectors, and we've done some math and some geometry and algebra with these vectors. Hopefully you'll get some good practice on the remote assignment with this. And then on Wednesday, we're going to talk about how to apply this to different examples that you may see in some of your first weeks of your physics class and maybe even in your calculus class. Okay, thanks for listening.